Everyone, and thank you for attending this talk about formal verification. I'm Romain Soulat, and I'm going to present to you a tool we've been building with Jean-Frédéric, Etienne, Alistair Hill, and Catherine Stacy. Imagine you've finally built your dApp. You have had this idea for days, weeks, months, maybe even years. It's finally done. You've built a smart contract. The interface is here. Everything is ready, and just before deploying on mainnet, you start to wonder, did we test enough? Is everything secure? Did my test suite cover everything? Did all the scenario, the attack have been covered by those testing suite? And yeah, am I truly safe? And today I want to show you that you don't have to trust that your testing suite and testing scenarios are covering enough. You should formally verify your smart contracts. So how do we verify programs? Well, the most classic way is to just run tests. You have a specification. For example, you have to build a foo function that just returns A times B plus A times C. Very simple. You write some piece of code, and you are a bit smart. You realize this is 3 operations. You can do it in 2. So you optimize. You're very proud of yourself. But now you wonder, does this code actually implements what was in the spec? And how do you do that? Well, you build unit tests. You're going to try a few scenarios. So 0, 0, 0 should return 0. You run your code. It returns 0. You're happy. You're going to run on different values. Positive 1, some negative, everything negative, maybe some very large values just to see what can happen. And when do you really stop? When is it covering enough? Here it's just unit tests, but you can imagine the same thing for integration tests when you want to verify whole scenarios for your dApp. So where you deploy, then you have a user that interacts, then the smart contract returns something to the user. Maybe you want to try some attacks with someone running some other transaction, like whole scenarios. And once again, you want to verify, is my smart contract, my dApp, behaving as intended? But the question is, when is it enough? Well, maybe never, and that's where we want to have formal verification. So what is formal verification? Formal verification is a way to verify your contracts, your programs, not for a given set of inputs, a given set of test cases or test scenarios, but all possible inputs. So for this example, you want to verify that for all possible triple of integer ABC, you're always going to return valid. You never want to find a falsified, which would mean there is a bug. You want valid. But so formal verification is a set of techniques and tools that can do this kind of verification mathematically and bring you the strongest guarantees you can have. So what is formal verification in practice? On our simple example, is just trying to realize mathematically if your implementation, so A times B plus C, matches your spec, so A times B plus A times C. And here is a very simple equality, and you want just to verify that. So if you were in math, like in high school, or maybe a bit before high school, this is something you can do with pen and paper, but how do you do something like that with a computer? That's why you use tools which are called proof assistant with their own dedicated language, and you can write the proof that A times B plus C is equal to A times B plus A times C. But just for this very simple formula, this is going to take like 45 lines of proof for something that is very simple that you can probably do in a couple of lines or by pen and paper. But to really get the full proof from the very definition of natural number, you need all of that. So now when you see that, you're starting to wonder, I'm not going to do something like that for smart contracts. If it's that long for a very simple formula, how many lines of proof, how many hours will you have to spend to prove that your dApp, to get the mathematical proof that your dApp is actually secure? It's probably massive. It's going to take you months or maybe even more. And that's where we want, with this tool, to bring something way different. We want you to be able to tell the tool that you're sorry, you're not going to write the proof. There's no way you want to write all of that. You just want to have an automated command that you can run, solve here for our tool. And this solve command is going to build the mathematical proof for you. Or if the proof doesn't exist, it's going to find something back to tell you. But the idea is that we want the user to not have to work that hard to get the proof, and we want to automate all of that. So our vision for the tool that we've been developing now for almost 1 year is that you write your code in your favorite programming language. It can be Icon, Plins, Plot.es, Scalus, UPLC directly if you're one of those developers. Then you push a button and you get proofs. How does it look like in practice? Well, as I've said, the developer just write their code in their favorite programming language. Here it's in Plinth, or what was known as Plutus TX before, but this is Plinth. Then you write some specification like we had before with this foo function that should return A times B plus A times C. Here it's a bit more complex because, well, it's a smart contract. And then we want, from that point, when the developer has done all of that work for us, I mean, that he was always going to do, but specifying is something that we're going to require from them. We want them to be able to simply call our tool on this file, and we should return the mathematical proof that their code matches their spec, without them having to write those very, very long proofs that we've seen before. But we want to bring even more to the user, because in those proof assistant, when you're trying to prove a theorem that's actually false, like your spec doesn't match your code, the tool is never going to let you know that what you're trying to do is false. It's going to let you try and try and try until you figure out by yourself that something is wrong. On very complex proof, this can take days or maybe weeks to realize that, yeah, I'm trying to prove something wrong. I need to rework all of that. So for our tool, we want to bring something more. We want to be able to output to the user that, no, this code is not correct. There is a bug. And we want to be able to provide a nice trace of execution, like a set of transactions that, starting from an input state, reaches a state where you have a bug, where your system is a deadlock, where you have a security vulnerability. So a bit under the hood, how does it look like? Well, the top is the user interface. This is where they develop their smart contracts anyway. So here we're considering VS Code for our work. And in this environment, the user is going to have to write their code and their annotation. And then from there, everything will be handled by the tool. How do we do that? Well, we have to translate to a language that can prove things about mathematics. So we are using Lean4, which is a very well-known language that you saw cut snippets from Lean4, but it's a very well-known language to do these kind of things. But Lean4 doesn't understand Plinth, doesn't understand Icon or Plot.ts or UPLC. So we need to first transpile those languages and those smart contracts into Lean4 so that we can get into a world where mathematical reasoning can happen. Unfortunately, Lean4 doesn't know about the Cardano blockchain. It has no idea what is a UTXO, what is a blockchain state, what is a transaction, what are the ledger rules, what is a CEK machine. So we had to bake that into the tool. We had to formalize the CEK machine. We had to formalize UPLC, all the built-ins. We had to formalize Plinth. What are the ledger rules? What are everything? So that now, from this point, you have in Lean4, so in your mathematical world, you have something that understands Cardano blockchain, that knows what's a valid transaction, that knows what's how a script validates, and it also understands what the user is trying to prove, so their smart contract and their specification. But here, if you stop there, you have what we had before, where you have to write this very, very, very complex proof. And we said we don't want that, we want automation. And one way to get automation in formal verification is to use automated theorem proving provided by SMT solvers. SMT solvers are tools. I'm not going to go into details on how they work, but basically they're able to tell you if a formula is true or if it's false. And they do that automatically. So that's what we want to use to get those nice results that we've seen before, valid or falsified, and a counterexample. SMT solvers are very, very powerful. They understand a lot of logic. They can tackle quite complex formulas, but not huge formulas. And that's why when we get this with everything about the blockchain, everything about CK machine, UPLC, Plutus Ledger API, the smart contract, the specification, what we have there is huge and will probably not be able to be handled by the SMT solver directly. So we had to write those very powerful optimizations that are going to reduce the size and the complexity of your system to just its core, what's really needed to prove your specification. Then we need to efficiently translate that, which is in Lean4, into a language that the SMT solvers can understand. So that's our translation from Lean to SMTlib. And a lot of interesting things happen there because it's not straightforward to translate from this very rich language to a much less expressive language, which is SMTlib. And a lot of things are going on there. But I'm not going into too much details about how we do that. If you're more interested, we presented that work at the Rare Evo Dev Days, which has been recorded, and you can see in much more details how we do that. Then we get into the SMT solver. That's our job is done. This is a dependency we have on other tools. We use Z3, which is a very, very powerful SMT solver. And the SMT solver will be able to analyze the formula that we provided, which represents the code, its specification, everything about the blockchain. And we'll be able to provide three kinds of results, either falsified, that means you have a bug in your code. And in that case, it provides a counterexample for you to analyze or debug. It provides, or it can provide a valid result, which means, no, your code is safe. It matches your specification 100% of the time on all the inputs, on all the possible scenarios, even one with very complex attacks in them. And then we have a third one, because the class of problems we're addressing there is very much undecidable. So we can't expect to always be able to say yes or no. We have an undetermined branch, and it's basically when your solver kind of gives up. It's either too complex for him, and he's going to let you know maybe early that he cannot handle this kind of formula, or maybe it will reach some kind of limits of your system, some timeout, if it filled up your memory and it cannot reason anymore. Everything we're doing there about optimizer and translation from Lean to SMT-lib, all the smart tricks we have there is just to reduce this branch. It's just so that the user very rarely sees them. But if you see them, that's not the end of the world. You can still get from that branch a Lean 4 goal, so a theorem like we saw before, but now you have to get to a formal verification engineer and ask him, oh, can you solve that one for me? We solved 99% of our specification. We know our code is correct with 99% of our specification. That's just this one very specific edge cases that the solver is not able to handle. All right, let's do a demo. Yeah, that's big enough. So in here, I took the our good old example, A times B plus A times C, but written in UPLC. So this is kind of like how it would look like for UPLC code that runs on chain. Here, it's not directly the UPLC. It's a Lean 4 representation of this UPLC code. But you have three variables, A, B, C. You do A times B, A times C, and you sum it. Then you have your theorem, which is just, is this code correct? So what we have there is simply, if I execute my program, my UPLC program on integers A, B, C, with some budget here, 41 steps, am I always going to get A times B plus A times C? And you could write the proof there instead of sorry, basically saying the two that you don't want to write it. You could write it. It's going to take probably quite some time to do that, and we're not really into that. We want some automation, so I can just call the solve command, which is behind is everything that I've shown before. This is where our tool really operates. And here we can see that it's not quite happy. It says falsified. So that means this is a counter example. It says if you plug in those values for A, B, and C, you're going to see that your code doesn't match your spec. The developer can analyze what's going on and find that, well, maybe, I don't know, maybe something happened in the compiler, or maybe they did an issue, they write it wrong in icon or plinth or whatever, wherever they built it. But it's not a subtract that should be there. It should be an addition. So if you fix it by changing add, I barely even finished writing the correct version, that now it's saying, yeah, no, that's correct. This code is exactly computing A times B plus A times C. Now let's say your developer has an idea of how to optimize that, because well, that's take 41 steps. He thinks he can reduce it even further, and he comes up with a new version of your program, completely new version, and he says, well, that's a correct version that also implements the same spec, but in a much smarter way. How can you verify that? Well, you just write the exact same thing. You say, well, this new program with fewer steps is always also going to return A times B plus A times C. Is doing it in a different way, probably, but it pretends that it also matches the spec. We can call the solver on that and see that, yes, it's valid for all possible inputs. So you've proven that this optimization, because you reduced your number of steps necessary from 41 to 33, is also a correct implementation of your spec. All right, let's have a look at maybe a more complex example to show you that we can handle complex stuff. So this is a slightly more complex program. It's a bit longer. It has a lot more inputs. And it's also a real piece of code that runs today on mainnet in a very well-known protocol. So if we grab that, and once again, we grab that from the compiler, we don't have to write that. The user will never have to see this clean version. We will specify how are the input, what are the inputs. So you have some integer, you have some ratios, you have to define the shape, how the encoding is done. And then you can start, okay, you also have to, you can define what are valid inputs because this function is not always called on any integer, any ratio, there are some constraints. But granted that you written your spec, here we have 6 functions, this theorem that completely define the behavior of this function. You can completely prove that no matter the inputs, which there were 7 of them, yeah, seven of them, no matter the inputs that you provide there, as long as they satisfy this constraint, your function, your UPLC program is always going to behave as intended. It's always going to give you the result as you expect. And if we, just to give you an idea of how much time it takes, I can just restart the file and we can kind of see how long it takes to prove completely the correctness of this function. So, yeah, that's done. We've proven all of those properties for this particular function in about 5 to 6 seconds. And then you get a complete proof. You don't have to run property-based testing. No, you just got for every possible input. And we can see, well, maybe I tricked. It always says yes. But if I change slightly one of the specification and says, for example, that no, the result should not be always, cannot be equal to 0, but needs to be lower than 0, then the solver will say, well, no, I found one particular instance with those values where the result is 0. And if you were to do property-based testing, finding in one of those cases, edge cases where it exactly reaches 0 might be tricky, and you might need to spend a lot of time doing property-based testing with enough instances until you reach a point where you can get this counterexample. But here it's almost automated. I mean, it's automated, but it's almost instantaneous. Yeah, under 1 second. So, a conclusion. We've shown you that we can apply formal verification at the source code level. If you've known formal verification and automated formal verification, you might be familiar with tools like TLA+, which are going to require you to write a sign model with your code. Here, no, we're directly taking the source code. We've showed how we take directly UPLC, but we will be able to do that with other programming languages. Formal verification here comes with very minimal efforts. We just require the user to write a bit of specification, but not at all the very complex and tedious formal proof that usually comes with formal verification. And with everything that we've done, the formalization of the Cardano blockchain, the optimization, the translation to SMTlib, everything comes with very minimal effort and in a cost and time-efficient manner. You saw that I proved this complex function in under 6 seconds, once I've got the correct spec, of course, but it's very cost and time efficient, and I don't have to write any kind of attacks or edge cases. Everything comes from just those few properties. And also compared to other formal verification techniques, like if you were doing direct formal verification in Lean or Coq or Agda, this comes with counterexample. You saw that when we changed something, it told us some values that you can investigate and discover which bug you had, where is the issue, and fix it and then rerun in a very short span of time. So the time between you implementing, you discovering the bug, fixing and getting the proof can be very, very, very small, and that's something that you usually don't get from formal verification. What we're working on, and sadly I didn't demo there, is an integration into VS Code, because a lot of our developers use VS Code, and we want to show them the result. We want them to be able to operate the tool from VS Code, but also to get the result directly in a very nice manner. And we've thought of several things. So I showed you on the side of on a web view in my VS Code, kind of the raw data from the solver. But here we want to build some nice table where we take this info and display it in a very nice manner. So here you could see traces of execution, one transaction, another transaction, and so on, with your datum, redeemers, and strip context, and be able to analyze what's going on and discover why on the last step there is a bug. But that's something that's very much standard when you have those kind of formal verification tool, automated formal verification tool. You very often get a table because they don't really know what you're trying to prove. They just know some values. But in our case, we know what the user is going to try to prove. They are smart contracts. They take transaction and they do something with the transaction. So we want to also build those very nice graph view of transaction, of series of transactions from input to output being consumed by another input, some script references used between multiple transactions in a very very readable manner so that the developer can understand the flow, what was going on, see all of their data in one nice view, and be able to understand why something bad happened at the end. Our roadmap for this year, at the end of this year, we want to release our first stable version with a transpiler from Plint, which we don't have at the moment. We only have a transpiler from UPLC. We want to have complete automated trace reasoning, so those series of transactions and not just one execution of the smart contract. The bulk of the work is already done. We need to tweak some things a bit better so that it works a bit better on the translation to SMT and how the SMT solver can work. We want to finish the VS Code extension with integration with those nice views to display counterexample and being able to operate the tool, pass flags, pass options directly to the tool without having to write those long command line. For 2026, we want to transpile from Icon and start supporting other languages. And we want also to have something that's going to help a lot the user, which is the automated common attacks verification. Because if you're just trying to prevent some attacks on your contracts, like a large datum attack or double satisfaction, it doesn't really matter what's inside. The formalization of the specification is probably going to be very, very similar, and we can probably template that and just have the user say, oh, on this particular smart contract, I want to prevent large datum attack, and then we will generate the property automatically, run the tool automatically, and get them the result. If yes, they are protected against large datum attack, or no, we found a way to get their contract stuck with a large datum. We also want to scale to very complex dApps. So for 2025, we mainly hope, and I think we'll get there, to be able to prove one instance of a smart contract. 2026, we really want to be able to tackle dApps with minting policy, with multiple validators that interacts together to offer the business logic that you're looking for. In 2027, we want to extend to other chains. So I mentioned Midnight, but if you remember the figure I had before, we have the core kernel that's pretty agnostic of what you're trying to prove. We had to explain to it what is the Cardano blockchain with all of the formalization. We can replace this whole box with another blockchain, with another set of ledger rules, with another even accounting model. We could be account-based instead of UTXO-based. We just need to redefine which blockchain we're running on, what are the rules of this blockchain. And if we do that, then we can prove stuff about other blockchains. So we want to tackle Midnight, but we could see a world where we can have the tool working on Ethereum, for example, or any other blockchain. Of course, continuous update and improvements, because the formalization we did for the blockchain, the Cardano blockchain, very much depends on what exists today. But if you have a hard fork, if you have new built-ins, if something changes on the blockchain or how the blockchain behaves, then we have to know that into the tool so that our verification stays up to date with what is running today on the Cardano blockchain. And if you're interested by using this tool, you can contact us at this mail address, AFV for automated formal verification, _early access program at iohk.io. Or if you're lucky enough to be with us today at Revo, I'll be around and you can just come see me and we can discuss. Thank you.